Okay, good evening, everyone. So today we'll start with week 9. So anyone went through the lectures? I saw a few people saying they have watched. Um, Yoshi, yeah, Ramak. Okay, I see few people have watched it. So any issue that you have faced in this week? Okay, so I'll quickly go through this like this chapter, and later we can discuss if you have any doubt. Anyone has any doubt in this week? Whoever has gone through the videos.
I have a doubt, but when you reach that point, I'll ask it.
Okay. Great. All right. So week 9, we have Perceptron. So we're starting with Perceptron, and we have seen that like you can use Perceptron only for linearly separable data set. Okay. So this is a very important point. So only for linearly separable data set, you can use the perceptron model. So when we are saying only the linearly separable data is on which we can run this perceptron algorithm, then what we are in a way saying is that only if you have a data set, so let's say you have a data set and there is some W which is giving you underlying W which is giving you this data set. And if you have, let's say, on one side of the point, you have all the data of the same kind. And on the other side of this, so first there's a line over here, right? And on the other side, if you have data set of the other kind, let's say label, if I'm talking about label plus one, label minus one. So let's say on this side, my label is plus one. And on this side, my label is minus one. So only if you have a data set like this, you can perform your perceptron algorithm. Okay. So basically, in perceptron algorithm, what we are trying to do is we are trying to model my what is the what is the probability of y is equal to one given x. Okay. So this is what we are trying to model here. Like what is this probability? Like given if you are given a set of features, what is the probability going to be if we have to check whether which class it can belong to? So the assumption that we make over here is that my probability of y is equal to 1 given x should be plus 1 if w transpose x is greater than equal to 0 and 0. So just write 1, okay? And 0 otherwise. It means otherwise as in like W transpose X, if it is less than 0, we are going to just write that it takes a probability 0. So this is the assumption that we are making for this classification. So, and and this perceptron algorithm can be run only for the data set which is linearly separable. I mean the data set which looks like this, right? Um, Now, when we are talking about the linearly separable data set, so what is this assumption, right? So, okay. So here, if you look at this, what are we trying to do? We are trying to classify a data set into two classes, right? Either it goes to the class one or it goes to the class zero. So in a way, this is a classification problem that we're trying to solve, correct? So in that case, like if you have to check like which W, and W is something that we are trying to learn. This is the weight. This weight is what we are trying to learn. So now we know that I need to minimize the loss, right? So our goal always is to minimize this. So if it's a classification problem, I need to minimize this loss. And in classification, I give the loss as indicate a function of h of xi is equal to yi. Sorry, not equal to yi. So the number of mistakes that your algorithm make, you just add it, and that's what the loss is when you have a classification problem. And this is a function h, right? And I is varying from 1 to n. And this h is basically, in this case, it's nothing but set of all the linear function. I'm going to look at set of all the linear function. Uh, but even in that case, like what we had said earlier is that still it's very hard to solve this problem. Okay, so solving this problem of minimizing your this loss function, it's still an NP hard problem. Even if you're just looking at the I mean the linear function. Okay, so this H is a set of all the linear function. But in perceptron, like there is an additional assumption that we have made, right? And that additional assumption is that the data set is linearly separable. I mean, there is some W which is able to classify your data set as plus one. I mean, the data is coming from one class and the data set is coming from another class. So it is able to perfectly classify my data set. There is some W. So if perceptron makes this assumption, and there is some W which makes no error, so I mean you have the minimum value that it can take in this case is it should be W, right? So if I add the linear separability condition, then this will imply that minimum of sum over indicator function. And now my h of xi is what? I am just going to look at the sign of my W transpose xi, right? So I'm just going to look at, sorry, sign of W transpose xi. If this is equal to zero, sorry, if this is equal to yi, exactly yi, then there is no error, right? So, mm, okay, yeah, not equal to yi. And I is varying from 1 to n. And this is, I'm saying I'm adding the linear separability condition. I mean, there is some W. So when we are saying there is the linear separability condition, it means we are saying there is some W which
And
belongs
here
to
it should
RD.
be sine of yi, na? Sine of W transpose X not equal to sine of yi.
But YI, we are just taking 1 and 0, no? So it's okay, right?
1 and minus 1 or 1 or 0, because here you have taken as 1 and
Uh,
minus 1.
okay, let's stick to 0 because here also we've talked about 1 and 0.
Okay.
Let's stick to this. Um, so when we are saying linear separability condition, it means we are saying that there is some W such that you are able to get the sign of W transpose Xi to be exactly equal to Yi, right? So if that happens, the error that we are going to make is going to be exactly, the minimum value that we're going to get is exactly, right? So this is what we mean. Now, uh, now what the perceptron does is, now we can start with our perceptron algorithm. So what perceptron does is, like, if you have a data set which is x1, y1, x2, y2, xn, yn. So again, like, this is a class. This comes under the supervised learning. So there should be the labels, and it's a classification problem. So all the labels that we are writing over here, all those features be in RD, but my YIs will belong to plus minus one. Okay. So this is my data set. Now what perceptron does is, now the algorithm start goes like this. So what perceptron does is you initialize the weight vector to be 0 first. Okay. So you initialize this to be 0. And we know that this is an RT. Okay. So initialize 0, W0, and until convergence. So when we say until convergence, it means when you reach to a point when your W is correctly classifying all the data point, right? When all the data set which has level is at one side and the all the negative level is at another side. So when we reach at the stage when my W is exactly correctly classifying all the data points, then we can say the algorithm has converged. So what we are going to do is, so until convergence, what we are going to do is, so we'll start with, let's say we have n data set. We are going to start from here, okay? So we are going to start, let's pick my first data set, and I'm going to check if my sign of W here for like which iteration you are done, okay? So before this, I was going to write one in any general data point. So let's pick some data point from here, and in general, let's say I have picked xi yi. Okay. So what we are going to do is, once we have picked this data set, I am going to check whether the sign of this WT transpose. So T is here to denote the number of iterations. Uh, Xi, if this is equal to Yi. Okay. So if the sign is, if the sign of WT transpose Xi is exactly equal to Yi, then we are going to do nothing, right? I will stop here. In case my sign of, or let's write, so if this doesn't satisfy, if my sign of WT transpose Xi is not equal to Yi, then in that case, we'll update our W. So we'll do WT plus 1 is equal to WT. So whatever our initial, like previous W was, weight was, we are going to add this Xi Yi to this W. And this is the update rule for perceptron. Sorry, please give me a minute.
Ma'am, what is the criteria for convergence?
Yeah. So, like as I said, the convergence mean your whatever W you get at the end, if your W is correctly classified to your data set. So, for example, suppose you have some data point, let's say one data point you have here, one data point you have here, and a data set of, let's say one data point you have here. So, this one is -1, and these we are saying the label is +1. I'm going to start with the W, which is W naught. Okay. So, like my initial W is W naught, and I need to check whether using this W naught, how many are being correctly classified, how many data points are correctly classified, and how many are not correctly classified, right? So, whichever data point is not correctly classified, uh, I'm going to use this update rule. And it's going to use update rule. So the thing is, at the end, you should be able to reach to a point where your W, so if this is my W, and anything on this side, it is going to, okay, not this. Okay. So anything on this side, it should be predicting +1, and anything on this side, it should be predicting -1. So if you come to a situation where this holds, right? So we can say that this has converged. I mean, my algorithm has converged. Now let's say initial W that you would have picked, that you would have gotten was something like this, and this is my W, right? Now, if you look at this W, ideally this point is correctly classified, but this is not correctly classified, right? So we cannot say that this W is able to predict my data points correctly. So we cannot say that this algorithm has converged. So again, you will have to, if this data point, my algorithm is making a mistake, then I will update this. I will update it using this tool, where I will do WT plus 1 is WT plus XI right? So whatever this XI is, I will just take it and multiply with sign and update it. And again, I will check whatever W I will get. Let's say in the second time, I get my W to be maybe something like this. Maybe the second time when I did, I got it like this. So again, I see that, well, this is being correctly classified, but again, this is not correctly classified, right? So again, I need to update my update, do this update, and at the end, I should be able to reach to a point. Well, it may not be even possible that your algorithm will converge, but uh, if you are able to reach to a point where I can say that my W is exactly able to predict what the labels are for the features, then we can say we have reached a convergence, just like in this case. So here we are correctly able to classify my data point. Hope that is
Okay,
clear.
ma'am. Yes, ma'am.
So if there are
Ma'am,
two,
Hmm.
no, if there are
ma'am,
two,
you can
oh, sorry, sorry.
Okay, one by one. Geeta, you go first.
Yeah. So if there are 2 points which are misclassified, then which xi yi would you consider?
Uh, I will do one example where I can show you. So if in case there was 4 point, let's say here you had another one was minus, you had a point which was minus. So even this is not being correctly classified on, and let's say on this side, you are left with one plus sign, plus one. So again, this is also not correctly classified. So in this case, I have these 2 points. One is this and one is this, which are not correctly classified, right? So again, I will update. So there should be some sequence in which you are going through this xi, So suppose this is my x1, this is my x2, this is my x3, this is my x4, and this is my x5. right? So suppose you were looking at this point x3, and I mean you were looking at the, I mean you had picked your x3 y3, and you checked that the sign of this is not coming out to be exactly to be right. So in that case, you did this update and you got this, right? So once you have got this, again, when you are going to the fourth point, which is the x4 y4, you are going to use the weights that you have gotten for this x3 y3 to do the update of for this x4 y4. And then you will go to what W you get using this x4, I mean this data point. Your weight will change, and so again the whether your x5 is correctly classified in that case or not, we don't know. So again we'll go to x5 y5, right? So you go in the sequence basically.
Okay, but you have to again redo for all the data points, or
Yeah, you
the
have
weight
to
is
read it.
changed.
Yeah, yeah.
Thank you.
Ma'am, there will
Hmm.
be change in final W's for both the cases.
Can you repeat? There will be.
There will be change in W's for both the cases if we start either ways. Picking either ways, xi and yi, there will be a change in W's.
Oh, you are saying if we pick if I pick my xi yi in some other way,
Yes, ma'am. There
is there
will be
going to be change
the
in
final.
W? No, I mean at the end whatever W you get, that will classify it correctly. So there won't be a change.
Okay, ma'am. Thank you.
So, ma'am, once you get a mistake, suppose you get a mistake here, suppose that
Mm,
W transpose Xi is not equal to Yi,
mm,
uh, sign of W transpose Xi is not equal to Yi, then you
mm.
immediately apply the update rule,
Update
right?
rule.
Without going to
Yeah,
the other points,
yeah. With
without going to the
the
other
other
points.
point, yeah. So whatever data point you have picked, you found a mistake, you do the update rule, and then whatever WT you get after this update rule, now you're going to use this new W for the next point that you're going to check for.
And we can scan the points in any order, na, we want. It
You
is
can
not
scan the
necessary.
points in any. It's not. I mean, it like it will depend. Like I mean, you can scan in any order you want. That's not an issue. But the same order you should maintain again.
Ma'am, but in this case, there is no W, I think we can have for like the.
There is.
And like in this case, there is so much miscellaneous
This is
points
not a
also.
linearly separable data set, he's saying,
Yeah,
the
yeah.
one which you have drawn.
This is not a linearly separable data set. That's true. Yeah.
So this algorithm will work
Maybe
for this or no?
no, not will not work for this. So maybe I should have drawn it. Think if I draw it here, it should work. It should be maybe maybe a little few changes. Maybe here I will draw. Maybe I don't think it will work even in this case. Uh, let's keep it here.
X3 can be -1.
This yeah maybe it this is -1.
Is it necessary to always pass through origin?
Not really.
So it is linearly separable anyways. Like before also
Uh,
it was.
So it has to pass to the origin, na, ma'am. Otherwise, we have to add a.
Your xi, yi will
then in
change
that
in each
case,
You can
you will
center the
have
dataset, no?
line. Line can move around.
then you can center the data set. That is one option.
Yeah, yes.
Uh,
And ma'am,
So
what?
is
mhm.
it like the where is the density of data is like one class is more, the weight will be higher. Is it like something like that?
What density?
Uh, I mean, like in the upper portion the +1 are more, and in the lower portion the negatives are more. So like it will decide the weights according to this. Like how is this algorithm working? I'm not getting.
Okay. So, I mean, this was just an example I was giving for this algorithm. So, okay, let's see this. So, suppose I have maybe a point over here, which is 1, 0. I can have a point over here, maybe 1, 1. I can have a point here. Let's say this -2, 0. And yeah, let's just these point. And let's label this as -1. So let's label this as -1. Let's label this as +1. And let's label this as +1 again. Okay. So now, what we are going to say is my algorithm said that you pick W naught to be 0, 0 first, right? All right. So now with this 0, 0, wait to be 0, 0, I need to check my W naught transpose x1. I need to check my W naught transpose x2, and I need to check my W naught transpose x3. Okay. So let's call this as x1. Let's call this as x2, and let's call this as x3. So if I take any data point you take, I mean x1, x2, x3, I know we are going to get all 0, right? Now, what assumption we had made for the perceptron algorithm? The assumption that we had made was um, predict probability of y is equal to 1 given x to be 1 if W transpose x is greater than equal to 0, 0 otherwise, right? So I know that the label for um, okay. The label for my W transpose, I mean this x1 is positive, right? So if this is positive, if this was positive, right here, this was positive, and so if this was positive, my W transpose x is anyways coming out to be so I can say that uh, I will predict this as 1, right? So there is no mistake happening over here. Yeah. There
So
is no
zero
mistake
you consider
happening.
as positive, right?
Yeah,
Zero you
positive.
consider as
Yeah.
okay.
Now, if you
If
look at
W
second data
transpose
point, yeah,
if
this
W transpose
is
X
again
is zero, then you consider it as positive.
positive. Yes.
Plus
So if I look at this second point, then again, this label is +1
No
and
mistake.
no mistake, right? So this is fine. But now if I look at and this was -1, so here you are getting a mistake because you're getting 0, no, which is wrong. So now this x3 there is a mistake. So what we can do is uh, we will update this. So now my
Ma'am,
W1,
for -1 we want 0, right?
hmm?
For -1 we want 0, right?
No, for -1 we don't want 0, no. I mean the
Like
label
in
for x3, label
yeah.
for x3 is -1,
Hmm.
right? But
Yes, ma'am.
it has come out to be 0,
Okay.
right? Your W transpose, what we are saying is my W transpose x, if it is less than 0, it should predict 0.
-1. It should predict -1.
It should predict -1. Yeah.
Yeah.
But what is happening?
You write the zero like
W transpose X, if
No,
this is
you have
equal,
written 0,
hmm,
comma W transpose X is less than 0. It should be
sorry.
Yeah.
-1,
yeah, if the y
comma
is
W
zero, then
transpose.
how you will
In
adding
the
the
second one.
x1?
No, no. Can you tell me what are you saying? Can
It
you
should
repeat?
be -1, comma W transpose X is less than 0.
It's okay. Okay. That's fine. No, you. What I'm saying is, you look at this. So what we're saying is W transpose X. If it is greater than equal to 0, then you should predict it to be 1.
Yeah.
What is
If
happening is that this is 0. Uh, but it was, I mean, you're getting it to be 0. The prediction is 0, but actually it was -1, which is a mistake, right?
mm,
So since this is a mistake, I need to update this, right? So now I will have W1 is equal to W naught plus um, X3 Y3, right? This we can do. Now what is W naught? It is just 0, 0. What is my X3? X3 is -2, 0. And what is Y3? Y3 is -1. So this is just going to be +2. So I'm going to get 2, 0. So now my W1 is coming out to be 2, 0. So this is my W2 is, this is my W dot we are getting. Okay. Now I need to see whether this is correctly classifying this, right? So you have checked for X3. Now, can we go and see what is happening for my data point, let's say X1, Y1? Okay. So what is happening with Xi, Y1 if I have my W1 to be, my weight to be 2, 0? So again, I will check W1. So W1 transpose X1. What is this? This is
2.
2, 0. One is 1, 1. This is nothing but 2. And it is greater than equal to
1
0. So
0,
it is,
ma'am. 1 0. X1 is 1 0, right?
okay, sorry. X1 is 1, 0. Correct. X1 is 1, 0. So again, you're getting 2, which is greater than equal to 0. So it should predict 1. And it is correct. It is correct. Now I will go ahead and again check for my X2, X2 by 2. So what will happen? It will be W1 transpose X2, which is 2, 0. Again, as we had seen, this is just 2. So again, this is 0. So it is fine. So this W that we got, 2, 0, is able to correctly predict my all these data sets. I mean, you did not even have to, I mean, do all this to check whether this W2 0 is predicting it correct or not. I mean, I could have just drawn this W on this graph, and I can see that with this W that I got, which is 2, 0, right? I can see that all my data points are correctly classified. They should be in the positive side, on the positive side. X2 should be in the positive, should be predicted positive, it is correct. And X it should have been predicted negative, and it is also predicting correctly. So from there also we can say now this W is predicting my data points correctly. Okay. So until convergence, until this happens, maybe for some example, you would not have reached the convergence at this stage. So again, you will keep on doing this, I mean, reiterating it and see at what stage, for what W, you are able to correctly uh, predict your data set, I mean, data points. Okay, this
And
is
don't
what
you
we
have to
need.
do it for X3 again, ma'am?
What
After the
can?
update rule, don't we have to do it for X3 again?
Not no, right? I mean, X3 if you do, okay, okay. All right. X3 you check. So X3 would be W1 transpose X3, which is 2, 0, and X3 is -2, 0. So this is what? This is going to be -4, which is less than 0, and it will predict -1.
Yeah, in this case it works up, madam, but
Hmm.
in other cases there could be a possibility, or it will never happen.
Uh, okay. So as far I have seen, if let's say there was a mistake coming in at X3, I was able to update this and found a weight vector, or found the weight. And if again I use this weight to check for the other data point, and again I found a mistake, then it is possible that the weight that I got for my data point X3 may not be correct, and I will have to reiterate and see.
Yes. No, in this case, since X3 was the data point that was having an error, so we have updated on X3 using X3, X1, Y1 of X3. So I was just asking whether we have to again recheck whether it has been classified correctly or not, or does it always
Yeah.
classify correctly
Um.
for the data point for which the rule
Hmm.
has been updated.
Yeah. Yeah. I think it will not always classified correctly. You will have to check.
Okay.
It's good to check. Yeah.
It may not be classified
So
correctly, right? So we have to check
yeah,
for
yeah. It
that
may
point
not
also.
be. Yeah. Yeah. So I see a question. Case of multiple time update tool, but point not correctly classify. Uh, oh, yours, are you, so Ronak, are you trying to say is if I, so are you trying to say that if if you did it, if you did the update tool multiple times, and if still your algorithm is not correctly classifying, how to do that? Is it?
Yes, ma'am.
See, if you have, I mean, the perceptron, oh, there is some issue with the my network. Is it?
Yes, ma'am.
Are you able to hear me properly?
Yes, ma'am. Your voice lagging.
Ma'am, now it's
It's
good, but previously it wasn't.
okay. Just let me know if it is lagging. Okay. Um, okay. So, Ronak, the thing is that the perceptron algorithm always converges. So, if you have a linearly separable data set, and there is another assumption that we are going to make. So, if your data set is linearly separable and that assumption is satisfied, another assumption we are going to make, the perceptron algorithm always converges. That's a theorem actually. So, it's not possible um, that you will not reach at a point, I mean, you will not reach to a W which will correctly classify. You'll always reach such W. All right. So this was about the perceptron algorithm. Now,
Ma'am, one doubt. Like
mhm,
previously in that diagram, which you have said
mhm.
classified, like this line right side will be +1 and this line left side will be -1. And in this diagram, what we can observe is the point is lying on that line also. So is it?
uh, Point is lying on the line also. Can you repeat? I think I missed few things that you
Like,
said. Can you repeat?
ma'am, like in the first diagram which you have drawn uh,
This one?
here, yeah, there you have said that -1 should be on other side and the +1 should be on the other side. And but in this diagram, what we can see is -1 is lying on that W.
-1
Oh,
is lying on this W.
okay, ma'am. Okay, ma'am. Got it. Got it. Yeah.
You got
That
it?
W is perpendicular to that line. Okay, ma'am. Yeah, ma'am. Got it.
Mm. Okay. Okay. So this
Here,
was
do we have
about,
to take the here? Do we have to
huh?
take the labels as 1 0 or 1 - 1?
Take the label as 1 - 1 because you are doing this, no? I mean, you're doing x3 by x3, right?
Yes, yes,
So if I take the label to be 0, 1, then in that case, if y3 is 0, you're only going to be left with W naught.
yes,
So
yes.
that's why assume y to be ±1. That's why even in the starting, I had written this that yi belong to ±1. Okay. All right. So this was about perceptron algorithm. Now next is that okay. So one issue that one can come across while doing this is that let's say the W that you had initially, the W that you had initially was maybe was correctly classifying most of the data point, but not correctly classifying, let's say, one or two of the data point. And for those data points which were misclassified, if you try to do the update, maybe you get a W, the new W, which is now going to misclassify more points than what it was previously. So, I mean, you do one thing. I mean, you try to uh, take care of one data point. It might affect other data points because the data is continuously changing. For example, in this question, um, it's a very simple question, so maybe not a good one to explain. So let's say I had, let's say this was my W. Okay, this was my W. Any data point that I will have on this side is, let's say, that is negatively labeled, that is -1. Consider one or two W that I got on the right side, and remaining on this side, I have positive labels. Okay, so this is how my data set looks like. So for this W, I am getting, I mean, these 2 points of mine are going to be misclassified for this W, right? So I will try to update the W, and maybe I got another W. Suppose that that another W is this one.
But
But
ma'am, this data
data
set
is
is
This is not a
linearly
linearly
separable.
separate.
Okay. Yeah, just maybe, yeah, this is really separable. Yeah, I need to
This
move it
also
a
is
little.
not, I think.
I'll just move it a little. Yeah, yeah, I think here it should work, I guess. It's okay. I mean, I'm not trying to be exactly correct here. I mean, in terms of figure. Um, but this is nearly separable, right? So maybe got a W, which so with this W, I'm misclassifying this data point. So now to correct this, I use the update tool, which is my WT plus 1 is equal to WT plus XI by I, right? So I get, let's say, another W, which is this one. Just for example, let's say this is my W dash. And for this W, now if I draw this hyperplane, uh, I can see that earlier where only one of my data point was misclassified. Now in this case, this one, this point, this point, this point, this point, and this point. These all now I have 5 data points which are not correctly classified. So again, I mean, even though you keep on doing it, if the data set is linearly separable with some proper margin, your algorithm will converge, right? But it may, like, you'll have to go through maybe more number of iterations in that case. So depending on what W, uh, like what, I mean, it will depend on like what W did we fix.
Is it possible like the number of iteration exceeds the n?
Number of iterations exceeds the
N. N means the number of data points.
uh, so there is an upper bound. I will come to the theorem. So after, okay, like after this, I'm just going to make one more assumption. So far, the assumptions that we have seen for one is the very first assumption was the linear separability assumption, right? Linear separability. Separability assumption. So when we said this, we said there is some W for which my sign of W transpose Xi is equal to yi. We are going to add one condition over here, and that condition is that is, it shouldn't be just linearly separable. It should be linearly separable with some margin. So, and that margin we are calling it as some gamma margin, where gamma is strictly positive. Okay. So, if I look at this figure, so suppose this is my W and this is the hyperplane. Now I have my data set, let's say all the data, I mean, negatively data point are on this side and data point are on this side. Okay, so this is how my data set look like. So I am going, so the what we're saying is since this data set is linearly separable, as we can see, but here it is not just linearly separable, it is separable with some gamma margin. So, I mean, this distance, or in this case, this one. Oh, so this is the margin that we're talking about. So we are saying it shouldn't be just linearly separable. Should be some margin with which it is linearly separable. Okay.
Ma'am,
So
both side is a equidistance. It should be
both side is,
equidistance.
because we're saying both are gamma distance.
Okay, okay.
So if this is my W, so I'll just write first. So what is mean by saying that your data set is linearly separable with gamma margin? It means that there exists some W star which belongs to RD such that my W star transpose Xi Yi should be greater than equal to this gamma. This is for all I and for gamma greater than 0. So this should hold. So what is mean by this? What is mean by saying that my W star transpose Xi Yi is equal greater than equal to gamma? So see, my Yi take the value plus minus 1, right? So if I take Yi to be 1, then what happens? It happens that my Y transpose Xi should be gamma, right? And in case I take Yi to be minus 1, I'm going to get Y star transpose Xi minus of this is equal to gamma, which in turn I can write this as W star transpose Xi to be greater than equal to minus gamma, right?
Yes, ma'am.
Right. So this line that we are seeing over here, So what this line basically is? This says that uh, you have I mean it will contain the set of all x such that my W transpose x should be equal to minus gamma. And if I look at this line, what is it saying is the set of all x such that my W transpose xi is equal to plus gamma. Right? This fine?
Ma'am, for the positive gamma, that the
Mhm.
line passing through the origin, that is the main separator line, it is less than that line, right?
So this, what is this line? This line is
W transpose
of
X.
all x such that W transpose x is exactly zero. What did you say? What is it about?
Then the positive gamma line,
Mhm.
it is greater than that W transpose X line, right?
I mean, I won't say it is greater in a sense. I mean, there is some shifting, right?
Yeah, some shifting is there, right?
Hmm. Right. This isn't boundary, right? This isn't boundary.
Hmm.
But now the dotted line that you see, they are my margins. So
Hmm.
what we are saying is just the data point to be linearly separable is not enough. So what happens is many times, like if you go through the go through the lecture, you will see that uh, there is one example given to you where your I mean your data points lie inside this boundary.
Ah,
Like let's say some data set a data point will lie here. Okay. So if that is the case, many a times, I mean, it's not, I mean, I won't say always true, but many times it happens that if you have a situation like this, it may happen that even though I can see the data set is linearly separable, they are not converging. So
yes,
that's why this
I got it.
additional assumption make it, so this additional assumption that
Hmm.
there should be a gamma margin over here. This makes sure that you are getting, I mean, your data set is linearly separable with some positive margin, then your algorithm always converges.
Yes, yes. Okay.
Okay.
Yes.
So this is the separability assumption with gamma margin. Now, another assumption that we have made is what we are calling it as radius assumption. So, what radius assumption says is your all data lie within a ball, some ball of radius r. So suppose you have okay. So suppose you have all your data set is against um, I mean the length of this is bounded by this ball, and this ball is of radius r. So it is not a right circle, but yeah. So this length of this ball, we are saying the radius of this ball is r, and we're making the assumption that all my data set is going to be inside this ball. Okay, for some r positive. So we are saying that for every I, which is for every I, my xi norm should be less than equal to r. Okay. This is the second assumption. And one more assumption that we're going to make is assume that my w star, the length is equal to 1. This is just for these are just for simplicity, these assumptions we are making. So we are assuming that the length of the W is equal to 1. Okay. So based on these three assumptions that we have made, we are going to prove the convergence of my perceptron algorithm.
Ma'am, in this figure which you have drawn, the dotted figure, the
This one
dotted
here.
line, the distance between the solid lines,
Yeah,
that is
this. This should
W
be
transpose
equal.
X equal to 0, W transpose X equal to 0, and the dotted lines,
Mm-hmm.
if that distance is if the distance between the uh, solid line and the dotted lines has to be gamma,
Mm-hmm.
then the W has to be unit vector, right? The W has to be unit vector, only then you can say that this distance between the solid line and the dotted line is gamma, right, ma'am?
Um,
If W is not the unit vector, then you cannot say
hmm.
that the distance is gamma.
Okay, I get that. Yes. Yeah, so okay. Like for example, I mean if we go ahead and solve for this, so currently we are just saying that um this W transpose X is equal to gamma. So I can convert this to a unit vector, right? Currently this is any W, but now I can convert this to uh, some vector W, which is, let's say, somewhere here. And this, let's call this as some maybe W star. And this W star is, we are saying that the length of this is, length of this is gamma.
Unit
So,
vector.
yeah, this is a unit vector. So, if, if my data set is linearly separable with this Gaussian, then this should hold, right? And if this holds, what we have seen is W transpose X should be equal to gamma. Now, what I can do is I can divide both sides by its length. Right? So if we can divide both sides by its length, so this the vector that we will be left with, which is W by norm of W, um,
This is W
transpose.
star.
This is my W star that I have written here. So this is my W star, right? This is my W star. And this is, which is gamma by norm of W. I can call this as uh, some gamma star maybe. So what we got is we have a W star transpose X to be some gamma star.
So the distance between the dotted line and the solid line is actually
And this
gamma star. Is actually gamma star.
is actually gamma star. Yeah.
Yes, yes.
Uh, hmm. Oh, okay. So,
Ma'am,
hmm,
explain this xi norm squared less than equal to r.
explain this.
Xi norm is squared less than equal to r. Yes, ma'am. Yes.
Ah, so the assumption that we are making is the length of xi is less than equal to r. I mean, the length of all the data, basically, all these data point, all these x's are in some closed ball that you have. So if you take all these x1, x2, let's say xn, and if you find the length of these vectors, I mean, you will have some upper bound, right? You'll have some, maybe the length of this is equals to, let's say 10, and everything in between is, let's say, less than 10. So I can say that all the, all the length, all my x's, it is upper bounded by 10. I can say that, right?
Yes, ma'am.
This is exactly what it says. I mean, all we are saying that, um, I mean, this is not the assumption for the perceptron, but this we are going to use for proving the convergence of perceptron. Okay. So, I mean, this is in general. I mean, this will always hold because if you have set of some data point, and if I have to take the length of every data point, then there will be at least one vector which is whose length is the high maximum, right? So I can say the length of all these data point is upper bounded by this R. I mean, all these data point are inside some ball, some closed ball, and whose radius is R. That's all we are saying.
Can I
So that
ask
is
Okay.
the
why?
outermost point.
What?
That was the outermost point. You can say
It
xn
is the
is the
outermost
outermost.
point. Yes, it is the outermost point.
Clear, ma'am.
Jatish. Okay. Jatish, yeah, go ahead.
Can I ask why this assumption is needed?
This assumption is, I mean, this assumption is not specifically for perceptron. I mean, but we will see this will help us in proving that the perceptron algorithm converges. Okay. I mean, even if let's say we don't call this as assumption, this still holds, right? I mean, I know that for every data point that I have, there will be some upper bound for my data point. I
There
mean, the
will
length
be
for
one outermost point.
yeah, there will be one outermost point, which will bound, its length will bound every other. So the proof is a little longer. You can see the proof once yourself. It's okay. Mm,
Yeah,
You
you
can
can.
let me know if you are not able to understand it.
Yeah, you can continue. I understand.
So I will not go through the proof of the I will not go through the proof that perceptron algorithm converges, but please go through the lectures and like next time when we meet, you can let me know if there is any issue with that. It's not very difficult proof, uh, but you should see the proof. So I will just give you the result for now that we get in the proof. So the result that we get in the proof is uh, there will be, the result that we get is number of mistakes that perceptron algorithm will make is um, is basically upper bounded. Number of mistakes perceptron algorithm will make is upper bounded by r square by gamma square. So if I call, if I say this number of mistakes that algorithm will make, if I give this using some L, so let's say L is a my Perceptron algorithm is making, and if this is less than equal to, and this turns out to be less than equal to r square by gamma square. So what we saw from this proof is that there is an upper bound on the number of mistakes my perceptron algorithm can make. And that upper bound is given by r square by gamma square. And since there is this upper bound of r square upon gamma square, we can say from here, so this implies that my perceptron algorithm converges. Since you are able to find an upper bound, okay? And we can say that my perceptron algorithm converges. Okay, so that was about the perceptron algorithm. Now, the next topic that we are going to see in this week is about the logistic regression. So, before we start logistic regression, yeah, Geeta, go ahead.
When you tell when you say that number of mistakes it makes, is it the number of update rules that are executed?
Yeah,
Okay.
yeah, correct, exactly. Anyone else has any doubt so far?
No, ma'am.
Okay. All right. So next what we have is logistic regression. Right? So when we were looking at the perceptron algorithm, we had made the assumption that the probability of y equal 1 given x is going to be 1 if my W transpose x is greater than equal to 0 and minus 1 if W transpose x is less than 0. We had made this assumption, right? Um,
Probability can never be -1, right, ma'am? Zero.
sorry. Yeah, sorry. Yeah, 0. So this is the assumption that we had made. And when, I mean, we were able to run the perceptron algorithm only on the data set which was linearly separable, right? If the data set is not linearly separable, we cannot run perceptron algorithm. So, like, how can we deal with such situations, right? So, can we relax this assumption that only if my W transpose X is greater than equal to 0, I'm going to predict 1, and otherwise I'm going to predict 0. Uh, can we relax this assumption? So, the question here is that, like before, we were like when W transpose X was greater than equal to 0, I was saying that I mean the probability is 1, otherwise it is 0. But this kind of um, I mean this model was not helping us in situations where data set was not reliable. So if we had all these negative points on one side and all the positive on one side and maybe one positive on this side and one negative on this side, this won't help. So what logistic regression does is it uh, it kind of provide a score which is a score which we are calling it as W transpose X. So it kind of for every for every X it kind of gives some score. So and that score is basically W transpose X. So if I give you any data point, any Xi I give, and there is some underlying W that is generating this data set. So I'm just going to give some score which is W transpose Xi to each and everything. Now, if like if we like relax the situation and we say we are going to allow uh, like not just say that I'm going to give 1 point, I mean any data set, I'm going to call it a 1 and minus 1, 1 and minus 0. Instead, what we can say is that any data point I see, let's say I have this data point, okay? So any data point, I should be able to label this data set as +1 or -1. And that will be based on the probabilities. Okay. Before that was not the case. So I mean, this is not a linearly separable data set. So let's say I draw a linearly separable. Uh, let's say this is all plus plus, and this is all minus minus. So in and if let's say this is my x1, x2, or let's say if this was the case, then any data point which is on this side, I'm going to predict this as +1, and anything on this side, I'm going to predict this as -1, right? So, but if we relax the situation, relax this assumption, what we are going to say is now any data point, I should be able to give, I should be able to label this as both +1 and -1 with some probability. Okay. So if let's say this data point is X. So there will be some probability with which I should be able to predict this label as +1, and there should be some probability with which I should be able to predict this as -1. Okay. So, and how do we give this probability is based on, so there is one, so again, how many of you know about the logistic function or sigmoid
Sigmoid
function?
function.
Yeah, you have heard about it,
1
right?
by 1 plus e minus some x, whatever
Yeah.
variable you're taking.
So yeah, so there is a sigmoid function which is g of z is 1 upon 1 plus e to the power minus z, right? And the graph of sigmoid function or the logistic function, it looks like, so again, this function will always lie between 0 to 1, right? So you have this z, and 0, you have 1. So the shape of this function goes like something like this. Okay, something like this it looks like. It should be a 0.5, but okay. Okay, just do this. Something. So it should intersect at 0.5, all right? So if you take, I mean, my W transpose X, right? This W transpose X can take any value. It can take the value as, it can go all the way to negative and it can go all the way to positive. So, like if some, if your W transpose X is exactly 0, I'm going to say that it can come with 0.5 probability either to class 1 or it can go to class -1, right? And the higher and higher your score is, so the higher this W transpose X is, more and more probability your model should be able to predict it as +1. And the more it goes towards the left, my model should be able to predict -1. Sorry, predict as 0, right? This
Ma'am,
is
0.5 is a threshold value.
I mean, no, I mean, we can't say it was threshold. This is how the graph of sigmoid looks like. It will depend on the, and what threshold you are putting it for a model. Maybe someone puts the threshold that only if I get the probability of y is equal to 1 given x to be greater than equal to 0.75, I'm going to predict +1. Otherwise, I'm going to predict as 0. The threshold is different thing. I mean, depending on what threshold you're going to predict as +1 or you're going to predict as -1. Okay, that is different. So from here, what you're just calculating in logistic regression, you are just calculating your probability of equal 1 given x. So given a feature, what is the probability that this is coming from? This will this will take y is equal to 1 is given by 1 upon 1 plus e to the power minus w transpose x. Okay, and this z that we have written, no, here, this z. So this z we are just calling it as w transpose x. So you can see here that as your z goes to infinity, so as this number goes to infinity, your um, so e to the power, so 1 upon something, that will be infinity, and it is moving towards 1, right? you can see that it is moving towards 1, right? And as your z goes to minus infinity, you are going towards 0, right?
And probability that y equal to 0 given x will be 1 minus this value.
1 minus, yes, 1 minus 1 plus. So this is probability that y is equal to 0 given x is 1 minus 1 plus e to the power minus w transpose x. That's all.
Ma'am, can we say that perceptron is like k means like in the ideology that in k means also we were having that we were strictly or like hard clustering it, that either it will be reassigned or not reassigned to that
Mhm.
cluster, and then we came up with k mean plus plus where we had a softer like probability 0 1. Here the sigmoid function will be also like a range of 0 1, not just like 0 or 1, yes or no into the cluster. So this logistic is like how we had the score for K-mean plus plus, that we have some little probability that it might also be from
Hmm.
the other side of the line.
Yeah, you can think it like that. Yeah. So here we are not restricting that each each x uh, each x is just one label. We are calculating both the probabilities. So whichever probability is higher, and depending on the threshold, you can predict as class 1 or class minus 1. So let's say if uh, if this probability that I was given a x, I mean data set, and given this data set, if I have to find the probability of y is equal to 1, and let's say I get this to be 0.85, okay, and if I put the threshold as 0.75, I'm going to predict 1, otherwise I'm going to predict minus 1. So according to this, I can predict this as plus 1, right? But let's say if it was 0.35 something, then I would have predicted it as minus 1. Yeah.
So y equal to minus 1 should be here, no, ma'am? P probability that y equal to minus 1 given x.
Yeah, I'm just writing it as something minus 1. Yeah, you can say 0. Okay. I've written 0, just write 0.
No, but in Perceptron, we are considering the labels as plus 1 and minus 1, right, ma'am?
Because there it was very restrictive because when you're doing the update, you need to multiply your data point with yi. So if I write there 0, it's going to cause problem. But here it's just about the label. No? Here it is not doing any, I mean, it is not making any difference because the probabilities I'm calculating just to x is x, right? So that doesn't matter. Yeah. Okay. So now the question is that we have all this sort of W's that are possible. So now we need to find the perfect W, which actually, suppose if you have this data set, whatever data set you have, let's say um, x1, y1, x2, y2, so on till x and yn, whatever data set you have. So now you need to find a W that has the highest probability of generating this set. So we need to find that W, right? So in a way we have to estimate this. And a very popular method that we know for estimation is maximum likelihood estimation. So we can use that to find our W. Okay. So if we use the maximum likelihood estimation, then in that case, the very first thing I need to know is what is the likelihood function. So the likelihood function will be L of W given X, right? And like W is a parameter that we know. And what we had seen is that probability of y is equal to 1 given x is given by 1 divided by 1 plus e to the power minus w transpose x, right? So if I have to find the likelihood function, uh, and you can see that your y can take the value either 0 or 1, right? The labels can be either 0 or 1 independently. So it is kind of Bernoulli distribution that you have. So when we have a Bernoulli kind of distribution, I know the likelihood function can be given by, so maybe this, let's just call this as g of W transpose x. Okay. So I know that it can be given by, so so this is basically probability, right? So if I write the Bernoulli distribution, suppose I have x, which takes a value 0 and 1 with probability p and with probability 1 minus p, right? So if I have data set coming from, the sample coming from this distribution, then I know the likelihood function is going to be this uh, p to the power xi, 1 minus p to the power 1 minus xi, right? So similarly, we can do the same thing over here because my y is just taking two values, 0 and 1, and the probabilities also are going to be 1, 1 minus p kind of, right? So this is my probability basically. G of W transpose is nothing but a probability. So I can write this likelihood function as the G of W transpose x to the power yi, right, times 1 minus g to the power W transpose xi to the power 1 minus yi. This is okay. My I is varying from 1 to 1. This is fine. So this is my likelihood function, and I know that my G of W transpose X is given by this. So just substitute it. And once you substitute it, so what we will get is 1 upon 1 plus e to the power minus W transpose Xi to the power yi times 1 minus 1 divided by 1 plus e to the power minus W transpose Xi, right? To the power 1 minus yi. Now we know that it's MLE, so taking the log is much more easier. So I will find the log of L, and when we do log of L at the end, I'll just write the final thing that we get after we do log of L. What we get is
Man,
we get
here should we multiply sign L of
where?
W plus S.
Sorry, correct. This is multiply. Sorry. Yeah. Like you're writing without log. Yeah. So the final thing that we get after taking the log is 1 minus yi minus W transpose xi minus 1 plus e to the power minus W transpose xi. This is log of LW is what we get. You can solve for it. It's not very difficult. So this is log of L that we get.
This way to maximize, right?
Yeah, now this we have to maximize. So what is log? I mean, Emily says that my W hat ML should be R max of W of W. Right? Now here my LW is sum over 1 minus yi minus W transpose xi minus log 1 plus e to the power minus W transpose xi. There's one more bracket here. Yeah. use this. So I is varying from 1 to n. So this is what we have to do now. We have to do our max of W. So we have to take derivative and we'll have to set it to 0 and everything we have to do. So let's say we take the derivative and what happens. So in this case, since we are talking about you have n different, we are not dealing with just one values, right? We are dealing with several variables. So you have xi, you have a vector. So now we have to do differentiation and all. So we can use a gradient, right? So when I take the gradient of, let's call log of LW to be small l of W, okay? So now I have to do grad of L of W. So when we do this, when we take the derivative of this, what do we get is, so one, so you have minus of W transpose Xi, which will be just minus Xi, which should be just minus Xi. And from here you will have YI Xi, right? Or minus YI minus W transpose Xi to be YI Xi, YI Xi. Then you have log of 1 plus e to the power minus W transpose Xi. So this is going to be minus of 1 plus e to the power minus W transpose Xi, right? And then you have to differentiate this term, which is e to the power minus W transpose Xi. So I'm going to write e to the power minus W transpose Xi. And now for W transpose Xi, we have to differentiate, and that is going to be minus of Xi. So you have minus of Xi, so it will make it plus Xi. This fine. So this is what we get, where I is varying from 1 to n. So if we expand this a little more, so what we get is, I can take, so I can just bring it front. So it is YI and Xi I take common for the first and the second term. So I am going to get minus of Xi, 1 minus e to the power minus W transpose Xi divided by 1 plus e to the power minus W transpose Xi. Okay. In fact, even we could have taken this term inside. No? Yeah. Okay. If I take Xi to be common, then you have Yi minus 1. Yeah, Y minus 1 plus of this, right? And just solve for this. What you will get is, if you look at these two terms,
Just
you
one.
will get 1 plus e to the power minus W transpose Xi plus e to the power minus W transpose Xi. Should be something is wrong.
And minus
Minus
sign,
one
ma'am. Minus
minus
sign.
e.
Minus or minus.
Can you repeat?
Minus one minus e. Then plus
This
e.
is minus C, right? I have taken
In the
Xi
starting
to
it
be
will
common.
be minus one minus e because there is minus one.
Okay. Correct, correct. Hmm. All right. So minus 1 minus C to the power minus W transpose Xi plus this. So it just gets cancelled out. I mean, these all cancel out. And we are just going to be left with 1 divided by this thing. So all this gets cancelled out. And at the end, we have I varying from 1 to n, Xi, Yi minus 1 divided by 1 plus e to the power minus W transpose Xi. Okay. This is what we get. So this is the gradient of log of LW. Now, what we have to do, we have to set it to 0 and we have to find this W. But if we try to do it, we are not going to get a very nice, I mean, there is no closed form expression over here when you like try to solve for W. So to deal with this, I mean, since this MLE is not, with MLE, we are not able to go to this closed forms. I mean, we're not able to get that inside W. So what we can do is we can use some optimization technique. So the optimization technique that we will use for this case is the gradient ascent algorithm. So in gradient descent, what we have seen is that my WT plus 1 is WT minus a step size times grad of log of LW. It would have been, right? But in since we have this maximization problem, so for the maximization problem, we can use the gradient ascent algorithm. So in that case, this is just one. So this is just plus one. What we are going to get is, so if I just write this, so you have I varying from 1 to n, xi yi minus 1 divided by 1 plus e to the power minus w transpose xi. Okay. So again, this yi is just the label, which is either 0 or 1. And I know that this is also just a probability, right? This is just, this was my probability, no? Which was given by G of W transpose Xi. And this Y is just either going to be plus 1 or it's going to be 0. So, uh, in a way, like if you subtract these two things, you're just going to get some scalar value if you subtract these two. So instead, what we can write WT plus 1, we can write this to be WT plus eta t times sum over xi eta I, where I is varying from 1 to n, where theta is some scalar. So theta here, so theta I is just r. So this is
Ma'am, here the W which we use to calculate that this second eta, this summation term, the W which we use is WT, right? Here the W which we use to calculate this term is WT, right?
yeah, I think I have not written it, no? Yeah, WT. So let's take this on down because up we are using for transpose. This is fine. Yeah. Yeah, this is for WT because for the THW we are able to write this. This fine.
So when we till when will we continue this gradient ascent?
So see, we had to find our W, no? But to find the W, the very easiest way, I mean, the very popular method that we know is we can use the maximum likelihood because we wanted to maximize this thing. We wanted to estimate this and we wanted a W which correctly classified most of the points, right? So we used MLE, but it turns out that like when we took the likelihood function, the everything, I'm stuck over here, right? Because of this e to the power term, the W that I'm going to get is not a very, it's not a nice W that we'll get. Okay. So to deal with this, I mean, since there is no closed form solution, no closed form solution for W, we move to this optimization technique. So what we are saying is we will use this gradient ascent rule, gradient ascent update rule, and from this we are going to find my W. We are going to
But
find my
madam,
W.
gradient ascent will never converge, na? Gradient descent converges, but gradient ascent, how will it converge?
What do you mean it will not converge?
Because when we are subtracting, then it slowly approaches towards the
No,
optimal
no.
W.
This is maximization problem, right?
Okay.
So we are trying to let's say some function we have. We start from some W and then I mean, we are trying to go up, right? We're not trying to go down.
Okay. Right.
Mm.
So we reach the local maximum here.
Yeah, local maximum will reach.
Okay.
Yeah.
So there we in gradient descent we will reaching the global minimum. Sorry, local minimum. Here we are reaching
Mm.
the
Local
local
maximum.
maximum. Okay.
Mm. So instead of like since MLE was not working, we can go ahead with gradient ascent optimization technique, and from there we can find our W hat. Right? So from there we can find our W hat. And now if someone gives me some test data point, some X test, which is an RD, and I can predict my Y test, right? Which is sign of W hat transfer X test.
It will not be sign, no, madam, because it will be 1 or 0, right? If sign will be used if it is 1 or minus 1.
So,
If W transpose X is positive, then we predict it as 1. If W transpose X is negative, then we predict it as 0, right? Not
zero,
1.
zero.
Yeah, maybe the indicator variable of the sign, something.
Yeah. So basically, what I'm trying to say is, you find the W using this optimization technique, and this is the W that we can use for this prediction.
So
So not,
you do W hat X test. W hat X
huh,
test. If W hat X test is positive, then you label it as 1. If W
mm,
hat X test is negative, you label it as 0.
yeah, yeah, right. So this was about the logistic regression. I see something.
Do we have to calculate this? Do we need to calculate this? Because label can either be 1 or 0, right? It will, okay, it's a probability, okay.
This is the probability.
Okay.
Oh, T is a hyperparameter. T is not a hyperparameter. I mean, T is the number of iterations, no? Yeah. Okay. So what we saw is that the issue that facing with the perceptron algorithm, where only the linearly separable data set, where we could perform the perceptron only for the linearly separable data set, the logistic regression is like able to tackle that problem. Like even if we have the data set which is not linearly separable, they are able to classify it properly. Okay. Any doubt you have? So these were the topics. I have left the proof of the perceptron, which I highly recommend you just go through it once. And if there is any doubt, we can take it in the next class.
I have a no doubt, ma'am.
Okay.
So in perceptron, we label it as -1 and +1. In this
Mm-hmm.
regression, whatever this, here we label it as
Logistic.
1 and 0.
Mm-hmm.
This is what logistic regression. In logistic regression, we give the labels as 1, 0, and in perceptron, we give the labels as 1 and -1.
No, I mean it's just label, right? I mean, why in Perceptron we took -1 instead of 0 is because
We use
it
that
it
update
helped in
rule.
its
Update rule.
update
That's
tool.
why.
Yeah, but at the end it is just labels, whether it
Yes,
is
yes,
+1
yes.
-1 or it is -1 1 or 0. Just the labels.
But it will in
But
the
in
theta depends on it, no, ma'am. Y minus something something.
Ma'am, this algorithm is also working like Perceptron, just we are dealing with probabilities like thing.
Sorry, can you repeat?
Ma'am, this logistic regression is also working like Perceptron algorithm, just we are dealing with probabilities as higher it goes up and low.
Yeah, but in perceptron, we were only allowing linearly separable data set. If the data set was not linearly separable, we could not perform perceptron algorithm.
Okay, ma'am.
Logistic regression also a binary classification, right?
Yeah, binary classification.
In name
Basically, it
regression,
is.
I think
Mhm. What?
in name regression, I think related to linear regression.
No, we call it a logistic regression, but it is actually a classification problem.
Yes, ma'am,
So
right.
regression is, I mean, the regression is there in the name because we are calculating the probabilities and it's real numbers, and that's how the regression name has come in. Because of this double transpose X that we're calculating. But at the end, we are doing the classification based on these scores and probabilities, all that.
Yes, ma'am,
Don't
also
get
one
confused
different.
with the names.
It is also what one difference. It is work with discrete and linear regression work with continuous.
What? Can you, linear regression works with continuous
And
and
logistic regression work with discrete.
uh, no. So see, regression problem is different and classification problem is different. No? In regression, like what we are trying to do is trying to predict some continuous, some numerical value to it, right? But in classification, we are just checking whether it belongs to class 1 or it belongs to class 0. You have the features given to you. At the end, your job is to, for each features, classify whether it belongs to class 1 or belongs to class 0, right? But in regression, what is happening? Any new test data set that come in, I'm going to get a real number, right?
Yes, ma'am.
Whatever regression model is.
logistic regression will work even if it is not a linearly separable data set.
Yes, it will work even if it's not really separable data set.
What will be the complexity
Complexity
of this algorithm? Logistic regression.
complexity, I'm not sure. I'm not sure about the complexity of this model. So usually like class regression, linear regression, they are less complicated model. But if I take you further, I think logistics should come after, it should be slightly more complex than the linear regression we could think of. And when you move further and further, SVM, perceptron, all that should come on more complex side, DL stuff, SVM, neural network. These are more complex models.
Complexity big O of ND. N is a number of data point, D is a feature.
Complexity of model is a different thing. We're not going into that right now. It's a completely different topic.
Yes, I'm right.
I have two more questions. Can you scroll a
Hmm.
bit down in the
Down. Yeah.
yeah? Can you go to the perceptron where you
Okay.
told the wait a minute? Yeah, linear separable assumption.
Mm-hmm.
The gamma margin. Yeah. Here
Mm-hmm.
you talked about something about the uh, W should be unit. Siddhartha asked something. I didn't get it. Can you please repeat that?
Mm. So, okay.
What did he
What
ask?
he ha no, no. What he asked is, um, we had said my data set should be linearly separable, but with gamma margin, right? And the definition of that is that there should some W star, there should exist some W star such that W star transpose Xi Y should be greater than equal to gamma. So based on that, so this is my according to this definition, this is my W star. So for this W star, I had a margin gamma, and I was able to write these two equations, right? Now, now what we are saying is, see, let's make this the length of the W where it was initially could be anything. Now make this length of W to be 1. Okay. So if I look at this, if this line, this is basically saying that of all x for which W transpose x is gamma. So W transpose x is gamma. So what I can do is I can uh, uh, divide both sides by the norm of W, and this will help me in like when I divide any vector by its norm. Eventually, I mean, this is expecting the vector to be of norm 1, the length 1, right? So that's why we divided it both sides by norm of W. And doing so, what we got is we got this W, I mean, this W upon a norm of W, which we are calling as W star. So this W star transpose X is now our gamma star.
Okay.
Yeah,
Okay.
yeah, this is what we are saying.
And this gamma star is exactly the distance between the
The distance
solid line and the border, this dotted lines.
border dotted line. Yeah.
So if we say that gamma is greater than zero always, so there is no case that
Gamma is always positive.
yeah, so there will be no case that the data point is lying on the decision boundary. If
No, no.
yeah, so we can assume that.
This is making sure, this gamma margin is making sure that there is no point which is lying on the decision boundary.
Okay. And I had one more question. Like the question was, can an in the number of iteration can you scroll a bit down?
Down. This one? Yeah. This one?
No. Wait a minute.
Number of iteration you're saying. Uh, Maybe here.
We are updating rule. Yeah, yeah.
Uh-huh.
So my question was, can the number of iteration increase the number of data points?
Can the number of iteration increase the number of data points? Is it what you're asking?
Yeah.
How can data points increase or decrease? Data point is fixed, no? You have xi, x1, y1, x2, y2, xn, yn. Data point is fixed. How can data point increase or decrease with the
No,
iteration?
no. I'm asking like,
Mm-hmm.
can the number of iteration like one,
Mm-hmm.
two, three, can it exceeds the n?
Or
Like
can it exceed n?
yeah, yeah.
So the number of so it is bounded by basically this. this value. Mm,
R square by
All
gamma.
that, all that we can say is that the number of mistakes that your perceptron algorithm can make is R square by gamma square.
Okay.
Maybe it can increase. We don't know, but we know that the number of mistakes that it can make is max R square by
Finite,
gamma square. I
finite,
mean, it's
finite.
number of finite number. But whether it is more than n, whether it is less than n,
Okay, cleared.
yeah. Okay.
Ma'am, in a real life example, how will we
Mm-hmm.
decide how small we want the gamma to be, or like how much we want the radius to be, so that the perceptron can work on it?
So there is, I'm not, I mean, how to decide this gamma. So it will, okay. I think we can choose randomly, I guess. Uh, it should be trial and error. But see, there's an extension for, I mean, there are various things where perceptron is not helping us. So there's an extension for this, and there we talk about support vector machine. And there we assume that this margin is, gamma margin is of length 1. But when we are actually doing the perceptron, I think it should be um, trial and error, maybe not trial and error. I mean, you have to see like which data point for which W your data point is the closest, and at least that much gamma you should have in your that much margin you should have, I guess.
Ma'am, actually we can have multiple lines like the separator
We can
line. We
have
can have multiple
um, no, no, we can have
with
multiple
different
lines,
gammas.
but we can have multiple lines. But what I'm saying is, whatever my decision boundary is, I will have to see which one is closest on both the side, no? So I mean, it shouldn't go much more beyond that. So max I can, if I look at this figure, all I can say is max it can be the maximum margin I can take is this much. But there can be many margin possible. I can have all these margins as long as it is non-zero and positive, right?
Okay, so first we center the data and get the 0, 0 origin. And then if the data points are like far apart from the origin, then we can have a more
Any
larger gamma.
not I mean you can take any margin, any small margin, significant gamma you take.
Even if it does not pass, even if you can make other lines which are passing through the origin, which will also separate the two sets, right? Uh,
We can make other line passing through origin.
which can also separate the two sets. Can't we do that, ma'am? Maybe the gamma will be lesser for that, but but still we can make more lines like that, right?
No, see, you just need a margin, no? I mean, you don't need too many margins. You just want a margin on both sides. And the margin should be just positive. And we are saying it is linearly separable with the tau margin.
Suppose you draw a different line. Suppose you make another line which is passing through origin, which is separating the two sets of
Uh,
points. You can make another line like that, right?
okay.
This is one line we have drawn, but we can make
So
another line
this
also,
is
which
my
is
decision boundary.
yes,
So you
yes.
are saying on the decision boundary, I make one more line. No, but like, what does it say? I mean, saying
Not on
that
the
tau
decision
margin, it says
boundary, but we can make
explicitly
another decision boundary also.
another decision boundary.
Another decision boundary which
So
will
I will
separate
draw,
the
I will draw I'll draw another figure. It's wait. This is bit messy. See. So what you're saying is, if I have this W, and let's say this is my W that I get, and this is the distance boundary that I get. Yeah, now can you tell me what were you saying?
Earlier we were having a distance of gamma on both sides. The points were separated by
Mm-hmm.
gamma on both sides, right?
Yeah, so I can draw that. So let's say this is my gamma margin, and yeah, this is my gamma margin.
So
And let's say
now
I also put
suppose you
some
draw
points.
a line which is slightly more slanted. Okay, right. So, suppose you
Hmm.
draw a line which is bit
Hmm.
more. I mean, between the y-axis and the line which you have drawn. Suppose you draw another line between the y-axis and the line which you
Like
separated line which you have drawn.
this.
If you draw another line,
Can you see this? Are you talking about
no,
this?
I'm not able to see your screen.
You're not able to see my
I think
screen?
there must be some. Yes,
Hold
now
on.
it is visible. Yes,
Now it is visible.
now
Okay.
it is visible.
So what you're saying is, huh? So you are saying is that I draw
Yes,
another
yes, yes, yes,
line,
yes, like that. Yes, yes. So this
this.
may be having a lesser gamma, but it is still a line which separates the points, right?
Exactly. So for
This is
if I
having a
draw
smaller
this,
gamma.
this is having a smaller gamma, right?
I
This is
think we
having
can
a
only
smaller gamma.
decide. We can only decide after we
See,
get that plane,
yeah,
that
yeah.
line.
So you will study the exact same thing, no? Once you go to SPM, I mean, once you go to next week, this is from where it starts exactly.
What is SVM, ma'am?
Support vector machine. So week 10 is support vector machine, and it starts from here actually.
Okay, okay.
Mm. Oh,
So we'll not always get the ideal. So will we always get the ideal separator using this perceptron algorithm?
uh, I won't say you will get an ideal, but you will be able to get a W which correctly classify your. But the margin can vary. I mean, how much margin do you want? That can.
So the line which we get is not the ideal line which is having the maximum gamma. It's not
Hmm.
guaranteed that it will be the maximum gamma.
Yeah, it is
The
not
line which we
guaranteed that. Yeah, yeah, correct. So if you look at it, I mean, the higher the gamma is, uh, with more confidence you can say that your W is doing a better job. I mean, if I get any new data set, since the gamma margin is high, now there is less chance that my algorithm will make mistake.
okay. But perceptron will always never. It's not guaranteed that it will give the best.
There is no guarantee that we get the best one. True.
It will just give a line which separates the 2 points with some gamma
With
margin.
some gamma margin. Yes,
Okay.
that's a good point. Um, all right. We'll close for today. All right. So we'll meet next week. Not next week. We'll meet for the solving test session. Okay. Thank you, everyone. Good night.
Thank you, ma'am.